To lecture 6. As usual, I request you to turn on your videos if you can. Again, not mandatory, but it would be great if you can. I think the Scribble link was shared, so I hope you're all well. Those of you who want to follow the notes separately can do that. So good. So last time, we saw the formulation of the unique games problem. We did some very basic stuff. We studied what the unique games conjecture is. And, we discussed lots of stories around it, basically, right? We did really no math. But, maybe some days we should do that. Today, we will do some math. In fact, some real cool math. In particular, we will discuss this strategy of rounding solutions to sum of squares, in particular pseudo distributions, especially ones that use higher degree sum of squares. And one particular application of this is the Aurora, Barak, and Stoiler algorithm for unique games, the statement of which we wrote down the last time. But there are like many applications. In fact, I'll focus completely on like a simpler application today for the whole class. And our plan would be to explore many more applications of this, and I'll sketch the unique games algorithm if I get a chance today, and then we'll discuss many more applications through homework. Not the homework 2, which is probably coming up tonight, depending on Peter and I, whether we get our act together. But hopefully, if we get our act together, then you'll have your homework 2 today. But in homework 3, we'll study many more applications of global correlation rounding, and by me I mean you. But we'll study like one concrete thing today, and it will be fun and interesting, hopefully. So just for the context, so far what have we done? We started our journey into sum of squares and pseudo distributions and whatnot by looking at max cut and other applications of the so-called Gaussian sampling lemma or Gaussian rounding, right? And we saw various variants of it for quadratic optimization. And, this was maybe like one nice way to, argue and reason about, what happens to degree 2 pseudo distributions over the hypercube. That was cool. Then, we said, well, we can actually do non-trivially better things with a degree 4 sum of squares. And so, for that, we use Gaussian rounding in combination with, this innocuous looking square triangle inequalities that you proved on one of the homeworks. And so depending on which version of the exercise you did, you either know a degree 6 or a degree 4 proof of it, but there exists a degree 4 sum of squares proof of this. So in particular, all the algorithms that we studied for the sparsest cut, or sorry, the expansion, computing expansion of a graph, use just pseudo distributions of degree 4. So that was one cool way to use more than 2 degrees of sum of squares. So today what we will do is, go one step ahead and see what's like a general method to use higher degree sum of squares. That's basically our goal.
All right, guys. Oh, you're back. Oh, okay. Wait, you're still muted, Pravesh. Pravesh, you're muted. I can't hear you.
Yo, can you hear me?
Yeah.
Okay. I closed all my tabs. I religiously closed everything. What is happening? Okay. How long was I gone?
Like 30 seconds-ish.
Okay, that's not too bad. That's not too bad. Yeah, maybe I need to get a new computer. Okay, all right. So I was mostly pontificating, so I'm going to do that again now. I said that, we studied like cool applications
You
of
can share
degree two.
Pravesh.
Thank you, Peter. Okay. Hopefully this won't happen again, but it probably will. Okay. Right. So far, we saw some cool ways to use degree two sum of squares, and in particular, one nice tool that we used here was Gaussian rounding and various variants of it, right? And we saw some cool applications. Then, in the class before the last one, we saw like a cool application of degree four sum of squares, and in one particular fact that we used about degree four sum of squares is that it can prove the so-called squared triangle inequalities, right? And they were a little bit innocuous looking at first, but then we discovered that they're quite powerful, right? Like we were able to give this non-trivial algorithm for computing expansion of a graph or approximating expansion of a graph. And actually, over this homework, you will study one more cool application, the homework that's coming up tonight, hopefully. So cool. So that was like basically ways to use degree two and degree four sum of squares. Today, we will introduce one extremely general and cool way to use higher degree sum of squares. Okay, and that's the so-called global correlation rounding. One application of this is the Aurora-Barak-Stoider algorithm for the unique games problem from last time. And I'll tell you a little bit about that. I will not do a whole proof of that in detail. I'll do maybe one part of it, which is extremely generalizable. In fact, my running example throughout the class would be completely different. It would be a instance of a certain restricted case of the max cut problem. So that's what we will do. And then, you will discover several other applications of this on the next homework. So homework 3, not 2. Good. So let's begin. So as I said, our running application would be the max cut problem on a certain special class of graphs. And in order to define this class of graphs, I need to tell you some very basic spectral graph theory. I'm going to close my Chrome just in case that was the culprit. Anyway, yeah, so we're going to study like max cut on a restricted class of graphs, and I need to remind you of some very basic spectral graph theory. So let me do that. So, as usual, we will think of G as a D-regular graph on n vertices. We just think of them without loss of generality as integers from 1 through n. So, let's maybe call this section, recalling basic spectral graph theory. Okay, so let G be, just a D-regular graph on n vertices, the object that we've been playing with for a while now. So I'm going to look at the normalized adjacency matrix of this graph. And that's just the following matrix. It's an n by n matrix where the ijth entry equals 1 over d if ij is an edge in G, which I'm going to just write as ij in G, and 0 otherwise. So, basically, I've just taken the usual adjacency matrix of the graph and just, scaled it down by a factor d. That's all I've done. If you studied or worked with random walks on graphs, and this is, same as the so-called random walk matrix of the graph, random walk matrix of G. And I'm going to recall facts that you probably already know, and in some sense, implicitly already kind of looked at when we were discussing expansion. But I'm going to need them explicitly today, so let me just recall them right away. So A is a symmetric matrix, right? So it has n real eigenvalues. So let lambda 1 bigger than lambda 2 bigger than so on up to lambda n be the eigenvalues of this matrix A. Okay. I'm going to make like super trivial observations. Observation 1, And I'll need your help to do this quickly. So while I write, please tell me the proof of it. Anybody, just like unmute yourself and tell me the proof. Tell me the proof that lambda1 is 1. Can someone just unmute themselves and tell me, please? Anyone?
The all ones vector.
All right, symmetry breaking by Tim over there. Yes, the all ones vector is an eigenvector. So it's a vector, with all ones in, in its entries, and it's an eigenvector. It's very easy to see. And in fact, the eigenvalue on that is 1. So is the corresponding eigenvector. Thank you, Tim. Don't unmute yourself. Don't mute yourself yet, because I need your help again. So here's observation 2. Lambda2 equals 1 if and only if G is disconnected. Okay, well, let me just, very quickly sketch why this is true. I'm sure all of you already know, but, in the interest of, just making sure that we're all on the same page. So suppose G is disconnected, okay? Then basically, to prove that lambda2 is 1, all I have to tell you is, is that there is, a two-dimensional eigenspace where, the graph, the A matrix, takes the eigenvalue 1, right? And it's very easy to define this eigenspace. It's basically, take, let's say, let's say, C1 and C2 are connected components. They can be more, but, let's say these two are definitely connected components. Then just take, the all ones vector on C1. So the rest of the entries are 0. Only the entries that corresponds to vertices in C1 are 1. And the all ones vector in C2, you can check both are, eigenvectors with eigenvalue 1. And they're orthogonal to each other because, C1 and C2, do not intersect. And that proves that, there's a two-dimensional eigenspace where the eigenvalue is 1. So lambda2 is 1. And the converse is also not that hard to prove. Basically, you can start from any vector V, which is orthogonal to the all ones vector. And from this, you can basically prove that this vector. So you can prove that V. So if V has eigenvalue 1, if AV is V, then Vi must be Vj if there is a path from I to J. You can prove this. And from this you can basically recover that that if lambda2 is 1, then in fact there must be two separate connected components, because otherwise you will end up with all ones vectors. So the only way you'll end up with, so the only way V is not equal to some scaling of all ones is if G is disconnected. Anyway, that's basically a very simple proof that lambda2 equals 1 if and only if G is disconnected. This probably is done in like the first linear algebra class or whatever, but if not, now you know. And we in fact saw some kind of a robust version of this in 2 classes before. We said that G is an expander graph, and then we defined this quantity phi G. And then we wrote down this theorem. We didn't quite prove it, but you will prove it in homework too. That in fact all cuts, all normalized cuts of a G are at least delta large, or random walk escapes every small subset of vertices in the graph with probability at least delta if lambda2 is strictly bounded away from 1. Okay, so that's great. So the first 2 eigenvalues tell you a lot about connectivity of the graph. One very nice example of such a graph is just a random deregular graph. Again, I don't want to define what a random deregular graph means, but there is like a natural model called as a configuration model. You can just Google search. It doesn't matter because I'm just telling you a factoid. I'm not proving anything about it. But it's an example of a very good expander. You can prove, in fact, that lambda2 for this graph is 2 square root d minus 1 over d plus something that goes to 0 as n goes to infinity. And in particular, if you make D large, then, the second eigenvalue becomes as close to 0 as you want. And so, it definitely fits this uh, expansion criteria that we defined above. So that's good. So random graph is an example of a graph where lambda2 is, strictly bounded away from 1. In fact, it can be made arbitrarily small by increasing the degree D. I want to describe a class of graphs that generalizes random graphs and expanders now, okay? It's a larger class of graphs, and it's a class of graphs that we will concern ourselves today. So for that, I'm going to make the following definition. Okay, and you'll see, so given the discussion, it would be pretty well motivated. So let G be a D-regular graph. And as usual, lambda1 up to lambda n are the eigenvalues of its normalized adjacency matrix. The row threshold rank of the matrix of the graph G, denoted simply rank row of G, equals the number of eigenvalues of G that are bigger than rho. Okay. So basically, I'm just counting the dimension of the subspace where the operator A takes an eigenvalue which is bigger than some number rho. Okay. So let's ask a question to see, if we are all following. So imagine that rho is, suppose rho is, example. Suppose G is an expander graph, and rho, is arbitrarily close to 1. What is rank row of G? Please unmute yourself. Please unmute yourself and tell me what this quantity is. How many eigenvalues bigger than rho does an expander graph have?
1.
Excellent. So the row threshold rank of an expander graph is 1. And so in some sense, you see why it's a generalization, right? Like if I look at all graphs with small threshold rank, it will certainly include random graphs, it will certainly include, expander graphs, but it would also include graphs which are not expanding. And in some sense, you can imagine vaguely that this has something to do with some coarse notion of how connected the graph is, etc. In fact, there is a not just a coarse but a precise connection that we will not see between threshold rank and some notion of expansion of the graph. But at least given our discussion, you see that it is somewhat related to how connected the graph is, and we are looking at graphs which are which are somewhat connected, right? It's like expander graphs are very, very well connected. We are looking at graphs which would have bounded threshold rank today. Okay. But anyway, like okay, so that's a good definition, and in fact, it's a good stopping point. So if before I move on and tell you the main running example of today, let me pause for 20 seconds and see if there are any questions about what we discussed. Completely elementary, but good to clear it away. Okay, good. So everything was clear. That's actually not a surprise. It's supposed to be simple, but also good to know that I didn't completely screw it up. All right. So now what? So now I can tell you what I'm going to prove today. I'm going to actually give you a better algorithm for max cut than the one we designed in the first class. Yeah, first class. For a restricted class of graphs, of course. So here is the running example for today. So let's maybe call this end of recalling spectral graph theory. Running example / main goal. So here's the theorem. Let G be a D-regular graph on N as usual. Let Fg be, the following function that you're all intensely familiar with now. It measures the probability of success This is super annoying, I'm sure for you as well as me, but we've got to soldier on. How much of it did you lose? Peter, my friend, inform me.
Oh, I don't know. I was looking at my scribble, so I
We
didn't
just
realize.
started DBA regular graph on N. The first state.
So I started writing down the theorem statement.
Yeah.
Yes, yes.
All right. Not totally sure what's happening, to be honest, but I'll open a ticket with Zoom, best I can do. Or maybe I'll shut down videos, which is annoying, but maybe that's better. Okay, let's try it one more time. If it doesn't work, then I'll, turn off videos. All right, so I was telling you about the running example / main goal of today before we were unceremoniously cut off, but at least I was. So let G be a deregular graph as usual on, n size vertex set. Let fg be, just this degree 2 polynomial that computes the sizes of cuts, so like number of edges in the cut for every x. And let R be, this threshold rank, delta threshold rank of G over this big enough polynomial of delta. Actually, I'm a bit unsure whether I got the right polynomial, but when we prove it, we'll see if it's correct. Then there is a degree R plus 2 pseudo distribution mu. Oh, sorry. Then given a degree R plus 2 pseudo distribution mu, can find a distribution, actual distribution x prime, such that expectation fg x prime, so the expected size of the cut under the distribution x prime is at least the max cut of G, or okay, that's not correct. The expected size of fg under mu minus something which is going to 0 as delta goes to 0. Okay, so let's make sure we understand this theorem before going ahead and spending the whole class to prove it. What is this saying? It's saying that imagine that delta is some arbitrarily tiny quantity, and you are interested in calculating the max cut of G, up to some plus minus additive plus minus something related to delta. What this theorem is saying is that, well, if you are on a graph where the number of eigenvalues that are bigger than delta are, let's say, about R, then in fact, you can take a R plus 2 degree pseudo distribution, and then under R plus 2 degree, so you can somehow round an R plus 2 degree pseudo distribution to an actual distribution on cuts, let's say x prime, such that the expected size under this distribution of the cut is basically within additive square root delta of the cut size under mu. Okay, so if you remember from the second class, then we know that such a pseudo distribution can be computed in about n to the O of R time, right? And so basically this is giving, so this can be thought of as n to the O of R time algorithm to compute additive root delta approximation. Okay, so in particular, if your graph is if your graph doesn't have too large a threshold rank, then this would be an efficient algorithm to get root delta close to the true max cut value. And one trivial corollary of this is that you can solve the max cut problem in fixed polynomial time on random graphs. In fact, on any expander graph, any good enough expander graph. So again, any questions on this statement so far?
Pravesh,
Yes.
do you need to multiply the root delta by anything? Like
Yes.
number of edges or something? Okay.
Yes, absolutely. Otherwise, it was way too good to be true. Thank you, Peter. Yeah, this is yeah, and in fact, this is same as 1 minus O of root delta times. So who can tell me why this is same as the second expression here? In fact, let me not even say squiggly inequality. It's in fact inequality. So who can tell me why this is also true? Again, feel free to unmute yourself. And do it before we are cut off by Zoom again. Well, the only observation required to conclude this, yes, Mitali, sorry, go on.
The E tilde mu is smaller than M.
No, that's not what, well, you need a lower bound on twiddle E mu G so the reason this is true is because, this guy is at least M over 2. If oh, sorry. So, okay. You guys didn't answer it because I asked a bogus question. Let me fix it. Same as n to the O of R time algorithm to compute 1 minus O delta multiplicative approximation. Okay, so this is a legit statement. The error I was making in asking the question was that the claim isn't true for every pseudo distribution, it's true for the optimal pseudo distribution. And the only reason why this is true is because, for the optimal pseudo distribution, this twiddle E mu of FG must be at least M over 2 because, there is always a cut in a graph which cuts at least M over 2 edges. So the optimal value must at least cut at least M over 2 edges. And so, if I take M over 2 minus O of root delta M, then it's at least 1 minus O of root delta M. Still good? Feel free to ask questions if not. Mitali, are you convinced?
Yeah.
Okay, very good.
So I have a question, a more general question for,
Yes.
let's just say the R equals 1 case for expanders.
Yes.
Are there combinatorial algorithms that do the same, that achieve the same bound? Or is this like really
Yes.
where like,
Yes, absolutely.
oh, there are, okay.
Yes. I mean, for max cut itself, it's very simple to, compute. Basically, max cut of a expander is easy to compute using many different algorithms. Actually, even for more general unique games problems, there are, more combinatorial algorithms that I think can solve even the unique games problem on, expander graphs. But actually, this observation applies to something even more general than unique games. It applies to all 2 CSPs. So you can use this, the framework we will do today, it will apply to even like general 2 CSPs on expander graphs.
Okay.
And that I'm not too sure that there is a combinatorial algorithm for.
I see.
So if you go general enough, then, this algorithm might actually be all that you have.
Cool. Okay.
So Pravesh, I have a question here. So I mean, I don't think that, for example, like 2 CSPs, like I mean, take the 3 coloring problem. I mean, I think that they are the most difficult on expanders, right?
So so our version of 2 CSP is max 2 CSP. It's what you're asking is a good question. So when you are looking at 3 coloring problem, which you're right, the satisfiability version is a 2 CSP. We are usually looking for, violating no edges. The max 2 CSP corresponds to the situation where you're trying to, find a, let's say 3 coloring that violates as few edges as possible. And we are measuring, multiplicative approximation. So if the best one, satisfies all edges in the sense that the graph is three colorable, then we'll be happy, with violating at most O of root delta edges, because that will give us a 1 minus O of root delta approximation.
I see. Yeah. Okay.
Does that make sense? Does that clarify?
Yeah. Yeah. Yes. Thank you.
Yes, of course. All right. So that's good. Hopefully this theorem is reasonable. And like one simple implication of this, by the way, is that, if you are looking for hard examples for maxcut, for example, examples for which, 0.878 approximation cannot be improved, the one that we proved in the first lecture or second lecture, forget. Well, the hard examples can never be graphs of small threshold rank because of this theorem, right? Like small threshold rank graphs are always going to be easy. So you must hunt for a graph which somehow has many, many large eigenvalues. Okay, good. So we will prove this theorem. In fact, this is just a simple example I chose to illustrate this so-called global correlation rounding. So we will, our main interest is really to introduce this rounding algorithm. And to introduce and study this rounding algorithm, I need to tell you a few basic properties of, that help you reason about higher degree pseudo distributions. So what we'll do is, next spend maybe like 30 to 40 minutes on studying some extremely basic proposition level properties of, higher degree pseudo distributions. So we'll study some basic properties of higher degree pseudo distributions. Excellent. So lots of definitions and propositions coming up. It may be slightly boring, but we are moving towards a good goal. So hopefully you are still motivated. So here's the first definition we'll make, and we'll define marginal of a pseudo distribution on a set S of variables. Okay, so here is what it means. Let mu be a pseudo distribution on plus minus 1 to the n, just like what we've been doing so far. Then for any subset S of n, mu given S. So I'm going to use this notation. This is mu, I write like a bar subscript to it and then write S. So mu marginalized to S, we can read this mu marginalized to S, is the following function. So remember, pseudo distribution was just a real valued function on plus minus 1 to the n. And that's what this is going to be, except this function will be only on the variables in S. Okay, is the following function. For any y, so now y is an assignment to variables in S, okay? So at any such y, this pseudo distribution takes the value which equals the sum of mu x over all x, such that when I look at the assignment under x to variables in S, then it actually equals y, okay? So basically this is saying, just look at all x's such that to this favorite set of variables of mine give the value y, just sum over the mu x over all such, x's. And that's what, mu marginalized S given y would be. And, if you know the definition of marginal of an actual distribution, this is simply, that definition ported over to this, pseudo distribution line. Nothing special has happened. We just like lifted a simple property, simple definition from probability, discrete probability, and lifted it into pseudo distribution line. Okay, good. So in particular, I want to note the following, corollary of this. If I look at, let's make it remark, because this is not even proposition level stuff. For all subsets U of S, if I look at the expectation under mu given S of the monomial XU, and it equals the expectation of the monomial under mu. I'm saying that, if I look at any U, okay, if I look at any U which is completely contained inside the set of variables S, then in fact, the pseudo expectation under mu given S of XU is same as the pseudo expectation of XU under the original distribution mu. As in, we have not modified the pseudo expectations of any monomial that is completely contained inside S. Okay. And now, while I write the next corollary of this, if anyone sees an issue with this, if anyone sees that this is not like, it's not clear to them, I'll prove it. Otherwise, I'm going to assume it. So you have like 45 seconds to tell me that you don't understand it. So let's say the pseudo distribution has degree R. So this is simply, applying linearity to the fact about monomials above. Because it's true for every monomial, it's got to be true for all polynomials of degree up to R. And degree up to R actually is not even necessary. I'm just like trying to reason about degree R pseudo distribution. So really, in some sense, the meaningful computations I can do with them are pseudo expectations of degree R polynomials. And actually, this is just true for every polynomial that depends only on variables in S. Again, any questions, feel free to stop me, okay? This is all simple stuff, but the notation can be confusing. So, if it is, then we should stop right now and fix it. Good. Very good. So here is the first proposition we'll prove about this. In fact, you will tell me the proof. So let mu be a pseudo distribution on plus minus 1 to the n. And let's say, it has degree R. Okay. Let S be a subset of n of size at most R by 2. So, that means that size of S is at most R by 2. Good. Then the marginalized pseudo distribution on S is an actual probability distribution. Okay, time to break symmetry again. Who wants to unmute themselves and tell me the proof of this? All right, Jeff, you seem to be nearing symmetry breaking, so you should go ahead and do it.
Oh, wait. It's local PSD, right? Is that the proof you're looking for?
Yes. Yes, I'm looking for something like that, but I'm hoping that you will only use things that we explicitly said / proved in the class.
Oh.
Okay, so Misha, go.
In the first week, we said like if you like double, like if it's like up to like if it's like 2n, then it's just like matches up perfectly with the problem.
Right. So Misha is recalling the following fact that we all should recall. We said if you have a pseudo distribution on plus minus 1 to the n, and it has degree at least 2n, then in fact it's an actual distribution. And we proved it in the class, remember? So here we are observing that, look, mu, so let's understand the chain of reasoning here. Mu was a pseudo distribution, the one that we began with, of degree at least R, okay? Now, we said that under mu, the expectation of any polynomial that only depends on the variables in S has not changed at all, right? Therefore, mu marginalized to S must also be a pseudo distribution of degree at least R, okay? On the other hand, S is a subset of size at most R over 2, which means that I have a pseudo distribution on size of S variables of degree which is double the size of S or larger. Well, I know then that in fact mu marginalized to S must be an actual distribution. Okay, hopefully you know that Verbo's English language proof was clear. I'll just write it down. Mu is a pseudo distribution of degree R, implies mu given S is also a pseudo distribution of degree R. Note all expectations of f are the same. So in fact, this is a triviality. Since S is at most R by 2, using that degree 2 are pseudo distributions on plus minus 1 to the S are actual distributions, we are done. Okay, very good. So this is kind of cool, right? It's a very simple basic proposition. And there are like several ways to prove it. In fact, like Jeff was pointing out some other proof of this by looking at the so-called matrix of moments. We'll look at, those kind of objects maybe starting next class or something. But today I wanted to, do this basic proof, that follows from a statement that we wrote down earlier. Even though this is basic, it's kind of cool. It's saying that, if I look at the pseudo distribution, if I look at a pseudo distribution of degree R, and now look at its marginal on any subset of at most R over 2 variables, well, then in fact, it is an actual distribution, right? So even though globally, it may not be a distribution at all, right? Mu can in fact take negative values. Its probabilities can be negative. Well, even then, when you restrict your attention to any subset of, at most R variables, R over 2 variables, then in fact, it must actually be a distribution. Okay, it's kind of a cool fact, and we'll use this today many times. So in fact, this motivates the following, definition / notation / name. For all S, mu given S is, for all S of size at most R over 2, we call mu given S the local distribution of mu on S. So for every subset of variables, there is this local distribution, and I can call it a local distribution and not a local pseudo distribution, well, because we proved that it's an actual probability distribution. Okay, very good. Again, anytime, because we are doing very basic stuff, then only the notation can be potentially confusing. So feel free to stop me, okay? Like, don't be shy. If you don't stop me, Zoom will. All right, so now I want to tell you, one nice operation that we can do to modify pseudo distributions. Okay, and this is the operation of reweighting. Again, if you see, we are taking some basic things that we can do and usually end up doing to actual distributions, and we are just like constructing analogs of them for pseudo distributions. And we are trying to understand, when are these analogs useful, interesting, etc. And in some sense, this is keeping in mind with the philosophy of the class, right? Like we want to somehow study the solutions of sum of squares relaxations of higher degree. Well, we are giving them all these names which resemble, concepts in probability theory. We better, import concepts from probability theory, because if we don't, then, what's the use of giving them names? And so, we're just like coming true on our promise, the promise that the notation / names already made to you. Yeah, we're encashing that check that I wrote to you, I guess, at the beginning of the class. So here's the operation of reweighting, okay? Let mu be a pseudo distribution of degree R. Suppose P is an SOS polynomial, so it's a sum of squares polynomial of degree R prime less than equal to R. Okay, so take any polynomial which is SOS. Okay, well, what can we say about the expectation of P under mu? Note, pseudo expectation of P must be non-negative. Hopefully you all see that, because P is a sum of squares polynomial of degree at most, R prime, and R prime is smaller than or equal to R. This is just basically, one of the most basic and in fact, almost defining properties of a pseudo distribution. And so, it must be non-negative. So that's good. Let's in fact assume further that, this pseudo expectation is strictly positive. So even though, it's always going to be non-negative, But I'm going to assume here that P is a polynomial where the pseudo expectation is strictly positive. Okay. Then mu prime is said to be reweighting of mu by P if mu prime x is basically, chosen to be proportional to mu x times px. So I'm basically, shifting mass around in this probability distribution, well, pseudo distribution. I'm saying, if the pseudo probability of x was mu x, I'm going to, make it now proportional to mu x dot px. Okay. In fact, the proportionality constant is very easy to compute. What should the proportionality constant be? Well, if I want mu prime to also be a pseudo distribution, so let's do this, scratch work on this side. If mu prime has to be a pseudo distribution, well then, pseudo expectation under mu prime of the constant function 1 must be 1, which means that sum over x, mu prime x must be 1. So that basically says that mu x px times some normalization constant z should be 1, right? And so this is, the left hand side is just equal to z times pseudo expectation of p under mu, right? Because that's what the definition of a pseudo expectation of a polynomial is. And so that tells us that, z must in fact be, need more scratch space, is simply 1 over the pseudo expectation of this SOS polynomial p. Okay. So in fact, I can mu is said to be reweighting of phi if mu prime. So let me in fact just write it with an equality. So this, I just give you a completely new function, a mu prime function, where basically, I just scaled a mu by multiplying it with this value of the polynomial p, okay? And then just normalize it so that the expectation of 1 remains 1, okay? That's what reweighting of mu by p means, okay? Very good. Now, let's understand, what happens to expectations of functions when I reweight, okay? So, remark. So the hierarchy of how complicated a thing is, remark is lower than a proposition. Remark is something that almost never needs a proof. So expectation under mu prime of any polynomial f, remember what the definition is. It's mu prime of x times fx. Very good. Which equals, now just apply the definition from above, mu x px fx over pseudo expectation of p under mu. Very good. And what is this? This is simply the pseudo expectation of the product of the polynomials p and f. Okay. So basically what this mu prime does is simply, if I have to take an expectation of a polynomial f, well, it basically outputs the expectation of this fixed polynomial p times f, which is a new polynomial because product of polynomials are polynomials, and then just like rescales it by, the pseudo expectation of the polynomial p. Okay, that's what a reweighting does. Okay, so we define first, reweighting as simply, what happens to the pseudo distribution, but in some sense, we also saw the effect of it in computing expectations now. Very good. So we understand what a reweighting is. Of course, one question that we're all wondering is, if we started with a pseudo distribution, is mu prime still a pseudo distribution? Like we've given ways to compute expectations with respect to mu prime, but we haven't really argued if it's a pseudo distribution at all. Okay, so let's do that. This, is a legit proposition. It has, I don't need to write down a proof, but it is simple. So suppose mu is a degree R pseudo distribution on plus minus 1 to the n. Let P be an SOS polynomial of degree at most R prime. and mu p is strictly bigger than 0. Good. Then the reweighting mu prime equals mu x px over pseudo expectation under mu of p is also a pseudo distribution. Pseudo distribution, but its degree, the only thing I can promise about its degree is that it's at least r minus r prime. So I lose the degree of the reweighting polynomial. Okay, so in particular, if like r prime happened to be, let's say, r minus 2, then, you know, once I reweight by this SOS polynomial p, then, you know, I actually get a pseudo distribution. And the only thing I can promise about it is that it's a degree at least 2 pseudo distribution. Okay, I don't know what will happen if you compute expectations of polynomials of degree higher than 2, but for 2, you know, it will behave like an actual pseudo distribution. Okay, so why is this true? Okay, exercise in basics. Okay, let's do it. What's the defining criteria? What's the meaning? What's an equivalent characterization of a pseudo distribution of degree r prime, a degree r minus r prime? Well, you know, we need to check that twiddle e mu prime 1 is 1, and 2, that twiddle e mu prime f square is bigger than or equal to 0 for all f of degree at most r minus r prime over 2. That's all I need to check, right? That all squares, you know, of appropriately small degree get non-negative expectations, and, you know, the constant function 1 gets the expectation 1, right? That's all I need to check. And these are like trivial verifications now. So let's write down the definition, right? We know that e twiddle mu prime of 1 is twiddle e p times 1. So remember, we are using this remark here. If I want to compute the expectation of a polynomial f, then we convinced ourselves that it's basically, you know, expectation of pf over expectation of p. So for the 1, it just becomes expectation of p over expectation of p, which is 1. So we are very good. What about the second property? So now, you know, we have to prove that this is non-negative. The only thing to observe is that p was an SOS polynomial of degree r. F is a polynomial of degree r at most r minus r prime over 2. So claim is that p times f square is SOS of degree at most r. Okay, it's just like addition of degrees. And because mu was a degree r pseudo distribution, this numerator must be non-negative. So we are done. So, all good. Again, feel free to stop me. I'm doing all basic stuff, and probably, you know, things that are not entirely clear where we are going, but we are going somewhere, and I'll tell you where in a second. But let me, you know, just make sure that, you know, we all understand what's going on right now correctly. So stop me if you have any questions. So why did I define reweighting? Well, because we are going to be able to do one extremely important, nice, special case of this reweighting called as conditioning. Okay, and we will use it later today. So I want to define this operation to you. Let mu be a pseudo distribution of degree r. Let S be a subset of size at most r prime over 2. Let alpha be any value, any assignment that I can give to variables in this set S. Okay. Then mu conditioned on xs equals alpha is simply the reweighting of mu by the polynomial f alpha x, which is 0 if x restricted to s is alpha, sorry, equals 1 if x, you know, restricted to s takes the value alpha, and 0 otherwise. Okay, it's basically a definition. So let me tell you what's going on, and then convince you that what's going on is just a simple reweighting. I want to take us to, if I had a distribution and I want to somehow condition it on an event. Okay, that's the operation I have in mind here. So in particular, I want to condition on the event. I want to condition on the event that if I look at the assignment to the subset of variables in S, then the assignment equals some favorite assignment of mine, alpha. So I want to condition on the event that restricted to variables in S, they get an assignment alpha. Okay, I want to condition on this event. All right, then and I would like to start from a pseudo distribution and produce a new pseudo distribution which kind of looks like what would happen if I condition on this event. If it's an actual distribution, you all know what it means. You all know what to do. And I'm just telling you now that in fact I can do the same even for pseudo distributions. And the way I'll do it is I'll take this polynomial f alpha. F alpha basically is 1 if if I look at its input and look at the coordinates in the set S, then in fact x sub S is in fact equal to alpha and 0 otherwise. So f alpha just picks out all the x's which do give the assignment alpha to the variables in S that I care about. Okay, then f alpha need not be a square, but f alpha square is f alpha. So f alpha square is certainly an SOS polynomial. What is the degree of f alpha? Well, f alpha in fact is a function of only variables in S, and because all functions on the hypercube have degree at most the number of variables, degree of f alpha is at most S. In fact, it's exactly S here, but I'm reasoning from like some abstract nonsense principles here. But you can prove that this particular function has degree exactly equal to S, and so f alpha square has degree at most 2 times S, and so this is simply a reweighting of mu by SOS polynomial f alpha square, and in fact the reweighting mu given xs equals alpha is a pseudo distribution of degree bigger than r minus r prime. This is just a special case of what we saw before. So this reweighting might have felt a little bit abstract, but one extremely nice example it captures is of conditioning a distribution. Later on in the class, we will study other applications of reweighting where the kind of reweightings we do are not conditionings. But today we are only going to work with conditionings. Okay. Again, feel free to stop me if there are any questions, because otherwise I am moving ahead. Good. No questions so far? Everything's awesome? All right. Okay, so what have we done? We basically saw that marginals of pseudo distributions of degree r on sets of size at most r by 2 are actual distributions. That was useful. We call them local distributions. And then we saw this operation of conditioning, and in particular the generalization reweighting that we saw. That's like a way to transform distributions to other distributions, pseudo distributions to other pseudo distributions, and we'll use it later on today. But that was the background I needed about higher degree pseudo distributions. Let's now come back to this running example that we had. Our goal was to somehow solve the max cut problem, or at least get arbitrarily close to solving the max cut problem on the so-called low threshold rank graphs, right? In particular, we want to somehow do this by rounding higher degree pseudo distributions, right? So let's brainstorm a little bit on how can we round and I want to focus attention on a very specific kind of rounding, okay? Or at least I want to give you like one very basic rounding. And I want to, so here's an example. Here's a simple high degree rounding. In fact, let's make it a definition. Let's call it independent rounding. So let mu be a pseudo distribution of actually whatever degree, I don't care. Okay. Let x prime be the following distribution, actual distribution. And it just, what I'm doing is I'm simply going to set xi prime equals to 1 with probability half plus set each xi prime independently. So I'm giving you a way to produce a distribution that uses some information about this high degree pseudo distribution that we have. In fact, it's a very simple rounding. It just ignores all possible correlations, etc., that exist between variables. Just says, I'm just going to look at like first order marginals, look at the means of each of the individual xi's, okay, and then just take the product distribution with the same mean. So take the distribution where xi prime and xi prime and xj prime are independent for all I not equal to j, and the expectation of xi prime equals the pseudo expectation under mu of xi. Okay. So note that this way of defining is just a way to ensure that expectation xi prime equals pseudo expectation under mu of xi. Okay. So this is basically round each variable independently. This is just a complicated and fancy way to write round each variable independently.
Application is the factor of half.
Absolutely. I did. Good. So this is just, this is just the strategy of rounding each variable independently. Just, take a product distribution which has the same first order marginals as the pseudo distribution, ignore everything, every other information that the pseudo distribution is giving you. It's kind of, it's almost like somewhat funny to call it a high degree rounding, but it's definitely one way to round a pseudo distribution, right? You can certainly try to do this. And we can ask, when is it good? So when is it good, for example, for solving the max cut problem? Okay, so our high level idea is going to be the following. Okay, we will first try to analyze the case. We will try to understand pseudo distributions for which this simple, completely trivial kind of rounding does well. Okay, and then we'll try to understand what can we do if the pseudo distribution does not satisfy this property that independent rounding works well. Okay, so remember our task is still to solve the max cut problem. So let's now try to analyze what happens if I just independently round. Okay, let's just do this. So here is a proposition. Expectation fg x prime. So actually, okay. Let x prime be independent rounding of a pseudo distribution mu of degree at least 2. Okay, then Good. So I'm basically giving you an analysis. I'm giving you, in fact, I think this is going to be an equality. So I'm just like, literally going to go ahead and analyze what happens when you independently round each coordinate, okay? And the analysis of the performance of this simple rounding is going to be in terms of this quantity, the so-called pseudo covariance, this big tilde standing, on top of the curve here. And so let me, define this, but it's by now, you should be able to guess what it should mean. So it should not be a big surprise, what's going to happen next. So
Sorry, Pavesh, is there absolute value in the covariance?
actually, no, there isn't. Otherwise, it would be great, isn't it? Great and false. Thank you. Yes. Good. So, it's basically what you think it should mean. So if I had an actual distribution, what would I do? I'll just take the covariance of I and j. I'm just going to, just apply pseudo everywhere I can. So it's simply, twiddle E mu of xi minus the expectation of xi. Well, ran out of space over there. Okay, it's kind of slightly illogical to write like what I'm defining on the right hand side, but you understand, right? This is what I'm defining. Like the right hand side is what I'm defining, and left hand side is a quantity, Hopefully it makes sense. So that's basically, what this covariance, pseudo covariance quantity is. Okay, and what I'm saying is, under this new definition, I can completely characterize what happens to the value of the cut function, expected size of the cut under the independent rounded distribution x prime compared to the actual distribution, actual pseudo distribution mu. Okay, and this is a very simple proof, so let me just do it and then we'll pause for questions. So by linearity, I only have to focus on a single edge, and you see, like, it's going to become a 2-variable problem. So what do I need to do? Well, let's just calculate these two numbers. What is this? What does this become? So this equals but remember, xi prime and xj prime were independent. So this, and xi prime and xj prime are supposed to be plus or minus 1 random variables. So this is simply equal to 1 plus 1 minus 2, the product of the expectations. Good. What about the pseudo expectations? Well, same thing applies. The first two terms are going to be 1 and 1. And in here, I just get, the pseudo expectation of xi times xj. And so now, all I have to do is understand, how these two quantities are related. So notice that xi prime xj prime square equals twiddle E mu xi minus xj square plus, well, what do I need to add? I need to add comes to the factor 2. But in FG, in FG, this xi minus xj square appears with a scaling of 1/4, and so that just gives me 1/2 here. And this is simply, so we now recall that exi prime equals. So okay, there's one more step, and writing it is easier than pronouncing it. So I'm just using that, the product distribution matches the marginals under mu. And now, I know what this is. This quantity is simply the pseudo covariance that we just defined. Success. All right, so now we are done by linearity of expectations or pseudo expectations. So we've completely characterized what happens if you round a pseudo distribution for max cut independently. Just like respect the first order marginals, forget about everything else. Okay. Any questions so far? So this theorem is telling us something intuitive if you think about it, right? Let's try to understand, let's try to, reason about what this theorem is telling us or this proposition is telling us. So imagine that so now, I have lots of terminology because I spent like, an hour telling you trivial things. One thing I have ensured is that I have words to express what I want now. So, I know that if I take, let's say, at least a degree 4 pseudo distribution, then in fact, if I look at any two variables, the distribution there should be an actual distribution. Okay. So now let's look at, the actual distribution that the pseudo distribution induces, okay, on, xi and xj for some I and j that appear in an edge. Okay. Because, I'm trying to compute the expected size, it's good to focus attention on only the pair of variables I care about. And I know that, for a large enough degree pseudo distribution, there is in fact an actual distribution that corresponds to it when I look at its marginal on, xi and xj. And now we're trying to understand, well, when is it good to just simply, round the pseudo distribution just to respect the first order biases. So let's look at, some extreme cases. If the local distribution of xi and xj were completely independent under mu, then would I lose anything? Well, I should not lose anything because the distribution simply is the product of its marginals, and that's what my rounded local distribution is also going to look like. So in some sense, I lose when the covariance is somehow large, and in fact not just large, it has to be positive. Okay, it's like the variables need to be negatively correlated to hurt me in this analysis, right? And that's not so surprising. Imagine that my local distribution just happens to be the following thing. It's uniform on 1, -1 and -1, 1. Okay, so with probability half, my local distribution assigns xi and xj 1 and -1 respectively, and with the remaining probability it assigns -1 and 1. Then under the pseudo distribution, this edge is always cut, right? The two vertices are always on two different sides. But when I independently round, they will end up on the same side with probability half. So in some sense, I have to lose here, right? And I lost here because the variables were very strongly negatively correlated. If I told you the assignment to xi, then the assignment to xj was, kind of fixed, and in fact fixed in the opposite direction. And so what this formula is telling us here is that, well, you're in trouble if the local covariances are, extremely large and negative. Okay, so that's great. we've done it. We did a trivial rounding, and we discovered that it's bad when distributions have high local correlations. So we've got to do something about it. What we will now do, and that's basically the main insight of global correlation rounding. So the above analysis, all it needed was a degree 2 pseudo distribution, right? Like you were only using the first order marginal. So the higher degree things were already, not at all relevant to us in doing this independent rounding. So the main insight of global correlation rounding is to start from a high degree pseudo distribution and produce a low average covariance pseudo distribution by conditioning it. So if I somehow could start with some arbitrary high degree pseudo distribution, and I could do some operation to it in order to make its average covariance small, and then do independent rounding, then I'll succeed. Right? So Okay, I'll stop for questions because I feel like maybe I'm not 100% clear. But the main insight in words is start from a high degree pseudo distribution, produce a low average covariance pseudo distribution by conditioning mu, while ensuring that twiddle EFG doesn't change much. So let's call this, I don't know, mu1. So the cut size somehow did not change much when I conditioned, while I would want to somehow make on average the pairwise covariance small. If this happens, then I can just independently round on mu1 and win. Okay, good. Let's pause and ask me any questions if there are things which are not clear.
Yeah, I have a question. Like, what do you mean by low average covariance here across the edges?
Good. Yes, I haven't defined to you. I haven't described that, but Jeff, as usual, is looking far ahead. And we'll get to that, Jeff. But this is just like the hand wavy part, which exists only for 2 or 3 minutes before I make everything concrete. But at least the plan should make sense. Make sense, right? So let's maybe in fact clarify. Actually, it may be good to clarify what notion of average covariance do we need to be small, right? So we just looked at this proposition, and what happens here is simply the sum of the covariances on the edges of the graph G, right? That's what appears here. In fact, if these are negative, then they hurt us a whole lot, right? So in some sense, our goal, so to answer your question, Jeff, I decided to change my mind and answer it right away. Low average covariance should simply mean the average over the edges, because that's what appears in the term that hurts us when we analyze independent rounding. So low average covariance is actually across the edges of the graph. So let's define the following quantity. Ij is a uniformly random edge. That's really all I need. So let's in fact control it from both sides, because certainly controlling this is enough, right? So if I could somehow start from a pseudo distribution mu and get to a point where this quantity is small, if for example this quantity becomes delta, then I can go back and conclude that I get something, then okay, so let me write it here. Then EFG of x prime would be at least E twiddle mu1 of FG minus some delta times m. Now if under mu1 the expectation of FG does not change much, then in fact that's what I get. And if delta is small enough, then basically I have actually done a great job of rounding max cut. Good. So hopefully that answered Jeff's question, and was a good actually excuse for me to make this concrete. More questions?
We were always assuming that pseudo expectation of xi is 0, right?
It's an excellent question. Yeah.
So the left hand side is always m over 2. That means we are just
right. So so remember how? So this is a good question. So let's answer it carefully. So Praneeth is asking, when we were doing Gaussian rounding, we were always able to assume that the first order marginals are 0. Well, then we are in trouble, because we are just simply returning a uniformly random cut all the time. That's what independent rounding on 0 marginal means. That's never going to do better than half. So we are in big trouble if that's all we can do. But remember, we ensured 0 marginals by doing an operation. Like, it was without loss of generality, because we modified the pseudo distribution. We said, what? We can take any pseudo distribution, and then we can somehow, we can do the following operation where we sample x And just like return plus or minus x with uniformly random, so we sample x, and we return plus or minus x with equal probability. And there is an analog of this operation that we did on pseudo distributions to ensure that the marginals are always somehow 0. We will not do that anymore. In fact, if we do that, then we are in big trouble. So we will now, in fact, like in some sense, the only way this independent rounding can do something non-trivial is when the marginals are actually sufficiently bounded away from 0. So in this world, we would want the means to be large. Means 0 is bad. Does that answer your question somewhat, Praneeth?
Yeah. So I was wondering,
Good
the
question,
covariance
yeah.
term we wrote, is it the same for the new pseudo distribution which has 0 means? So given any mu, we defined it as mu of x plus mu of minus x by 2, right? We defined a new pseudo distribution which would have
Exactly.
0 marginals.
Right.
So is the covariance for mu and mu prime same?
Wait, what is mu prime?
I mean, that mu of x plus mu minus x by 2.
Good. The covariance is not the same. In fact, the covariance for the new so okay, let's write down things because we have the benefit of having memory here. So Praneeth is referring to the following operation that we kind of almost did offhandedly, and it almost like I swept it under the rug, saying, well, it's a simple thing, we can always do this. Let's look at it because it's kind of careful. It's important for us to look at it carefully now. We said, okay, take any pseudo distribution mu, and we can do the following. We can define this new operation mu2, let's say, and mu2 of x is simply mu of x plus mu of minus x over 2. Okay, this is what it means to sample. Okay, it's obviously bad language, but let me stick to it because this is kind of the point of it, right? Like we've got to use the notation and language we've developed. So we're going to sample the pseudo distribution, take x, and just like output plus and minus x with equal probability. That's what this corresponds to, right? This operation ensures that E mu2 x is 0. That's great. That's not so surprising. But it completely messes up the covariance. The covariance is simply the second moment. The second moment of the two distributions is equal, but the covariance is not. Okay. So notice that XX transpose, because it's a homogeneous quadratic, it doesn't change at all if I flip the signs of x's, which means that expectations of XX transpose and expectation under mu2 of XX transpose will be equal. But notice that if the means under mu were non-zero, then this is not the covariance. And well, it's a big tilde over it because it's a pseudo covariance. But the second moments of the distributions are preserved in this transformation, but the covariances are not. That was, I guess, the point of this discussion. So let me maybe write it here. Under symmetrization, second moments are preserved. Covariances are not. Good.
Yeah, this is what I was wondering about.
Yes, absolutely. Yes. Glad we cleared it up. Yes.
Yeah.
All right. More questions. So so let's maybe do this. Okay. We'll take a short break. We'll return at 5:37, 5:38. But I'm still around here so we can answer questions. So Peter, is there anything in the chat that somehow needs answering?
No, Misha had a question on like what things you could condition on, and the answer is just like you need the pseudo expectation to be like greater than 0. He was kind of like, I mean, basically the moral of the story is like if you're thinking of this like conditioning on an event, then like the pseudo probability assigned to the event
Must be non-zero. Yes, yes, absolutely, yes. So yeah, okay. So I suppose I did not quite clarify that we can't condition an event that does not happen. And it's true in probability and it's true in pseudo probability, the theory that we are painstakingly developing here. So I guess it's good to maybe explicitly point out that this makes sense. Suppose, oh no, I can't quite write here, but let's write it here. Yes, so I can't condition on an event that does not happen, but so yeah, that's definitely true. It's good. Anything else going on? Okay, all right. So right, so we before we stop for the break, we were just basically characterizing what is the condition under which independent rounding fails to give us a good approximation, good additive approximation to the max cut, right? And we discovered this quantity which was average of the covariance, the pseudo covariance, over all the edges of the graph. Let's make this into a definition because it's kind of nice to give things names. That's kind of all we have done so far in some sense. So yet another definition. Let's call it local correlation of a pseudo distribution. So let mu be a pseudo distribution on plus minus 1 to the n. I don't really care about its degree, so let me not even mention it. Let G be any graph on, vertices 1 through n. Then the local correlation of mu under G is the following quantity. It's literally, the quantity we care about. So it's no big surprise that I'm making this definition. It's this quantity, average absolute covariance between, pairs that appear in edges of the graph G. So G is, GVE. Guess I've been using E for edges all along, even though I didn't quite write it, but you all understand. That's my definition of a local correlation. And so now, we can summarize the discussion that we just had is that, independent rounding fails when the local correlation of the pseudo distribution is high. So let's also write that down. So summary of discussion so far. Independent rounding fails to give an additive delta approximation whenever, actually this is if and only if, because we literally computed the approximation ratio. But because I'm taking absolute values, it's maybe stated only one direction. So if independent rounding fails to give an additive delta approximation, then this average absolute covariance, when averaged over pairs that appear as edges in the graph, must be 2 delta. That's the summary of our discussion so far. And well, remember that. Okay. So now our insight was that we basically want to somehow use this higher round pseudo distributions and use this operations that we have to make on it, like reweighting, conditioning, whatever, in order to reduce its local correlation in the new language, right? That's what we would like to do. But this should in general be impossible. So who gets to unmute themselves and tell me why I cannot expect sub-exponential time algorithms to find pseudo distributions that maximize size of a cut in a graph, while have low local correlation, as low as I want. Why can't I have this? feel free to, break the symmetry and, unmute yourself. Oh, but I guess maybe somebody's answering on chat. Jeff Shu says ETH. Well, right, absolutely. So exponential time hypothesis says that, you can't solve 3-SAT in too little O of n time. And, basically, I guess I can't expect you to know the result, but if I tell you, you won't be surprised either, that there is no polynomial time approximation scheme for max cut, meaning that there is no polynomial time algorithm in n that for arbitrarily tiny epsilon gives you 1 minus epsilon approximation to the max cut in a graph. Okay, so there's no such algorithm. In fact, under ETH there cannot be such an algorithm that runs in time 2 to the little of n, not just polynomial time. While on the other hand, the discussion we just had shows that if I could somehow compute a pseudo distribution with low local correlation, arbitrarily low local correlation in sub-exponential time that maximizes the cut in a graph, then I would be able to round it using independent rounding, the one we just discussed, and actually get an arbitrarily good approximation to the max cut in a graph, additively speaking. But because the pitas for max cut is NP hard, in fact, under linear or quasi-linear size reductions, under the exponential time hypothesis that we defined the last time, this is not gonna be possible. Good, but we're not gonna try to make that happen either. We're going to try to make it happen for the kind of graphs we have today. And the key idea is to instead define a version of the correlation, which is, does not depend on the graph. It's a certain quantity that is, defined for the pseudo distribution in general. So make this cool definition. But to make this definition, I need to do a little bit of information theory. So let me maybe summarize where we are and then go there. So can't expect to find pseudo distributions of low local correlations for arbitrary G. Instead, we'll define a different global notion of correlation, global as against not local across the edges of a certain graph. And then we'll relate this global correlation to local correlation under the family for the family of graphs we like, and relate GC to LC for nice graphs. Okay, and to define this global correlation, global notion of correlation, I need to tell you or recall basic information theory. So here is another nice detour. This is going to be short. Okay. So we are only concerned with binary variables, but on your homework, I am going to ask you about some generalizations. So let me introduce these quantities somewhat more generality. So I'm going to look at random variables, or basically I'm going to think of random variables on q to the n. Think of q as just some integer, fixed size integer, like 10. So this corresponds to this is a space of assignments for 10 alphabet CSP, right? That's what this is. Alphabet of size 10. Okay, so let x be a q value random variable. So x be a random variable on q. Then this is a discrete random variable. The entropy, which I'm sure all of you have seen, of x is simply sum of the probability of I occurring times log of the probability that I occurs. Sure, you've all seen this before. That's what the entropy is. What I really care about, however, is understanding some notion of how far from independent are two random variables on Q. Okay, you saw we were looking at covariance, etc. And in general, we are happy when pairs of random variables are independent. I'm sorry about the sun, but hopefully the screen is fine. So a very nice information theoretic quantity that it allows us to measure distance from independence is the mutual information between a pair of random variables. And that's just equal to some ij in Q, the joint probability of x equals I and y equals j times log of probability, the joint probability, divide by the probability under independent distribution with the same marginals. Okay, so I'm just gonna like give you a different formulation of this because that's what's going to be nicer for us. But this is just well, I hope I didn't make a minus. I think this is fine. Good. So in order to reformulate this notion of mutual information and like be able to intuitively reason about it, let's remind you of conditional entropy. So conditional entropy of x conditioned on y is simply the average entropy of the random variable x conditioned on y taking a given value. Okay, again, I'm sure all of you have seen these definitions before and have some some feel for them, but if not, here's something that's like nicer and enough for us. What happens to the conditional entropy if, so note, let me write it like this: if x and y are independent, then what is h of x given y? Well, because they're independent, the distribution of x given y equals I is same as the distribution of x. So this is simply going to be equal to h of x. Okay, so the conditional entropy actually equals the entropy if the two random variables are independent. Okay, good, remember that. And in terms of the conditional entropy, the mutual information between x and y can be written as simply hx minus hx given y. So this is asymmetric, like I is like a symmetric definition, like I of y y semicolon x is same as I of x semicolon y. So actually you can prove that this is equal. But again, I'm not going to do any information. I'm not going to prove any information theoretic facts for you. Here is one nice interpretation though, which again is relevant for us. We just argued that if x and y are independent, then h of x given y is actually equal to h of x, right? In that case, note I x y is 0 whenever x and y are independent. Okay, so this mutual information between two random variables is 0 if they are independent. In general, the value of this mutual information is at most the entropy of the two random variables. And so this number, the larger it is, it somehow tells us that there are more correlations, and and somehow it's a notion of you can think of it as measure of how far from independent are the two random variables. Measure of how far from independent are x and y. Okay, so in some nice way it measures how far from independent are you. That's good.
Quick question: is the converse true?
Good. Yes, it's also true.
Okay. Thanks.
Yes. So just to say that clearly, x and y are independent if and only if the mutual information between them is 0. So that the reason I stated it as an if and only if because I forgot which side was the converse. So it's an easy way out to just state it if and only if. But okay, I hope I answered that question. I guess I'm not going to use scale divergence, so I will not define it. Okay, let me just state this fact. Here's a fact, and this is a very simple proof. So if there is time at the end, I will prove it. Otherwise, I ask you to take it on face value. So covariance of x and y is at most. So okay, let's state this. Let x, y be q valued random variables. Then covariance of x, y oops, is at most some order 1 term that depends only on Q, square root of the mutual information. In particular, I can bound the magnitude of the covariance between a pair of random variables by up to constants, something that grows as square root of the mutual information between them. In particular, if I have made the mutual information between two random variables small, then the covariance, the magnitude of the covariance between them will also be small. Okay, and again, this has like simple proof based on like this some basic inequalities in information theory. If there is time at the end, we will do it. Otherwise, I will post the proof on Ditto. It's very simple. It's like 4 lines, but I want to do it right now because I guess I'm running a little bit short on time.
Pravesh, like this constant is just independent of Q, right? It's
Actually, yeah, you don't even need Q. You're right. This doesn't even. Yeah, you're right. You're absolutely right that you don't even need Q. I think here. Let me state it with Q because it seems like that's the weak proof I wrote down in my notes. But you're right. I think I am clearly just being lossy here. So I think the Q can be removed. I think you're right. But again, we are going to work with Q equals 2 today, so it doesn't matter at all for us. It might matter to you on the homework, so I'll post the correct version on Ditto. Good. All right. So very good. So we did some basic information theory. We're all educated in information theory now. So we can go ahead and define this quantity that we referred to so far. This is the global correlation of a pseudo distribution. And it's very simple. The global correlation of a pseudo distribution, I'm going to write GC of mu, is simply equal to the average over all possible pairs. There is no graph anymore, just I'm taking average over all possible I and j of the mutual information between xi and xj. Let's say, let mu be a pseudo distribution of degree at least 4. Good. So it seems like I did a bait and switch on you. So let's make sure that we all understand what's happening here. Said, look, I did information theory for actual distributions. Then I said, I'm going to take mu to be a pseudo distribution, and then without even like telling you about it, I just wrote down this quantity I mu of xi semicolon xj. What does that mean? Mu is not a distribution, but we have convinced ourselves that if I look at the marginal of mu on I and j, ij is a set of size 2. So if I have a pseudo distribution of degree at least 4, then mu marginalized to I and j is an actual distribution. And then this quantity makes perfect sense. We've defined this quantity, for this pair of random variables xi and xj. And when I write down I of xi xj for a pseudo distribution mu, I actually mean the mutual information between xi and xj. With respect, like for where the joint distribution on xi and xj is the marginal of mu on I and j. Okay, so this quantity is well defined. So let me assert that it is well defined because you all know why. And then I'm just taking average over all possible pairs. Okay, so the outside expectation, there are lots of expectations that happen in these lectures, but this one is a real true one. It's the beast that we are most familiar with. Even though we developed a lot of pseudo probability theory today, this is the usual probability theory, the boring one. Cool. All right. So you all understand this notion. It kind of makes sense. It doesn't have much to do a priori with local correlation that we just defined. In fact, there are like 2 baits and switches I did on you. One, I kind of explained to you that it's actually fine. The other is that I define local correlation in terms of size of covariances, like magnitude of covariances, while I define global correlation in terms of this mutual information. There is a way to do everything in terms of mutual information, but this makes my life simpler. And to people who are familiar with global correlation rounding, you know what's happening here. But just permit me this leeway. This is just nicer for the proof, even though aesthetics indicate that I should have used mutual information to also define local correlations, and I can do that. It just makes my calculations a little bit more messy. So like think of from our perspective, we just like wanted to round max cut. We discovered that the quantity that matters to us is this expected over all possible edges of the size of the covariance. We just like pulled that out and made it a definition. And then now this is maybe like that was well motivated. This is kind of by fiat. I'm just using the power vested in me as a lecturer here to make this definition. And now we will use this definition to make some progress on this task of getting locally uncorrelated distributions, even though local and global correlations are defined under like two related but different metrics. Very good. But before relating local correlations to global correlations, I do want to point out that for this weird notion of correlation, we always generically succeed in finding pseudo distributions of low average correlation. Okay, so even though we can't always succeed for finding local distributions with low local correlation across an arbitrary graph G, we can always succeed in finding a pseudo distribution with low global correlation. Okay, so let's prove that. It's a very simple lemma. In fact, the reason I used the information theory was because the proof of this lemma becomes one-liner. So let mu be a pseudo distribution on plus minus 1 to the n of degree 1 over eta plus L. Okay, that's a funny way to write degree, but again, permit me just leave it because you will see why I'm doing that in a second. Then there's a reweighting of mu with degree wait, let's make it 2 over eta with degree 2 over eta sum of squares polynomial such that reweighting mu prime, oh let's not call it, okay, whatever, such that GC of mu prime is smaller than eta. Okay, and mu prime, okay, sorry, reweighting mu prime of degree at least L. So the reweighted distribution has degree at least L, and it's a reweighting done with a polynomial of degree 2 over eta. This fact is not surprising because the fact that it's going to be a pseudo distribution of degree at least L is just a consequence of the simple lemma we proved earlier. But I'm going to obtain this mu prime by reweighting mu with a degree 2 over eta SOS polynomial. And the consequence of this reweighting would be that the reweighted distribution would have small global correlation. Okay, very good. Any questions till I find my notes? Ah, there they are. Okay, good. So this lemma has like a very simple proof, even though I still need my note for it. What we're going to do is, basically define a algorithmic way, or define an algorithm to, find this reweighting. Okay. Here's how I'm going to do this. So we'll build a sequence of reweightings. Mu 0, which will be the starting distribution, then mu 1, and so on up to mu t minus 1, etc. And we will prove that so these reweighting. Okay, so let's maybe say this way: we will build a sequence of reweightings. Each mu t will be a degree 2 reweighting of mu t minus 1. So I'll successively reweight pseudo distributions. each time just by a degree 2 polynomial. And the sequence will contain at most 1 over eta different reweightings. And I'll prove that one of them works. That's enough to prove the theorem, okay? So let's call it mu 1 over eta. Each mu t will be a degree 2 reweighting of mu t minus 1, good. And one of them will work. Good. So here's how I'm going to do this. Sample a uniformly random 1 over eta tuple of variables from n. Let's call them I1 through I1 over eta. Now for each 1 less t less than 1 over eta, sample xit from local distribution on it under mu t minus 1. I'll discuss all the steps in a second so that all these kind of make sense. Then I'm going to set mu t to be the reweighting, which by the way is a conditioning. Good. Yeah, that's it. That's my procedure to define a sequence of reweightings. So let's make sure that you are all on the same page here. So what did I do? I'm just going to choose like a uniformly random set of 1 over eta variables out of n. Okay. And now I'm going to just like, successively reweight by conditioning on an assignment to these variables in a sequence. Okay. So it's like first, obtain mu1 by conditioning on a random value of xi1. And what value should I condition on? Well, I'll sample. So, at each point of time, mu t minus 1 will be a pseudo distribution. Okay. If I look at the marginal of this pseudo distribution on one variable, it's always always an actual distribution. I'm going to sample xit from that marginal. This is same as basically, draw an actual distribution with, the same expectation on plus minus 1 as the pseudo distribution mu t minus 1, and then condition on the value you just drew. Okay. Notice that this ensures that the event I'm conditioning on happens. So, like in other words, if I look at the expectation of this polynomial indicator of the event xit equals alpha t, then it is non-zero. Otherwise, I can't quite do this process, right? What is the degree of this polynomial? Well, it's a function of one variable. So, its degree, once I square it, cannot be more than 2. The square ensures that I'm reweighting with an SOS polynomial. So mu t is a degree 2 reweighting of mu t minus 1, correct? And in fact, this is the conditioning because because my polynomial is an indicator polynomial of assignment to a bunch of variables. In fact, just a single variable, right? All good? Right. So I have a sequence of, reweightings, and I'm going to show to you that one of them basically, satisfies the conditions of my lemma. Okay, good. So how am I going to prove it? One of mu i's works. So the idea is, to track a potential function. So let's define this potential function. It's the average entropy under the mu t distribution of a uniformly random variable. Okay, so for every t, I can sum up, basically I average out the entropies of the, the marginals on single variables. They're actual distributions, so these are like well-defined quantities. I'm going to use this as a potential function. And so here's like, basically the basic intuition is the following. If you are, if in some sense, so why are we doing this whole process? Well, we are doing it because the distribution had high local correlations. So large global correlation, right? What does global correlation mean? So high GC means that, average over IJ, this is just simply opening up the definition of the mutual information between Xi and Xj is large, right? Because if it was smaller than eta, then we would be done. So let's assume that, for T less than equal to 1 over eta, this condition holds, that the mutual information, the average mutual information between Xi and Xj is large, right? Otherwise, I'm already done, right? One of them already works. Still with me? Good. So now what's the idea? Well, we're saying, if the mutual information is large, then, if I look at a typical variable, right, by averaging, a typical variable should satisfy that expectation over J of I mu T Xi Xj is large. This is just saying that, if the average over all possible ij's of I Xi Xj is large, then there must be some I such that if I look at the average of mutual information between Xi and all the other Xj's, it must be large, right? Still good? Very good. So now what does it mean? Now, what happens when I condition on Xj equals to a uniformly random value? Well, the conditional entropy after conditioning, so H under mu T of Xi is basically the conditional entropy under mu T minus 1 of Xi given Xj. In expectation over the assignment I condition on, H of mu T of Xi is basically going to be H under mu T minus 1 of Xi given Xj, right? Now we already know, so now let's try to understand how much has it dropped. H of mu T, H under mu T of Xi actually equals, sorry, wait, let's like this, H mu T minus 1 of Xi minus H mu T of Xi. How much has it dropped? Well, this equals H mu T of Xi minus H mu T minus 1 of Xi given Xj, right? This equals the mutual information under mu T minus 1 of Xi Xj, right? So now if I average over all variables, over all, sorry, what did I do? Yeah, if I average over all I, and I took, okay, I think I messed up I's and J's. Sorry, let me fix it so that this makes sense. So let's, sorry about this. I'm just making notational changes. You're all there, but I switch my I's and J's, unfortunately. Good, finally. This is J, this is still J, J given I. And now I have expectations over J. Okay, good. Sorry about that, but I just switched my I's and J's. Now that I think about it, maybe switching it earlier would have been easy, but I'm already done, so let's go with that. So now, if I was a typical variable, then we know that, the average of the mutual information between Xi and Xj under, mu sub T minus 1 is at least eta, right? Which means that this is at least eta. What does it mean? It means that the new entropy, the new average entropy of Xi's must in fact be smaller by at least an eta compared to the previous average entropy. This means that the potential function has fallen at least eta. On the other hand, how much can the potential function maximum be? Like xi is, wait, what did I, were they bit variables or qvary variables? Oh, plus minus 1 to the n, very good. So the average entropy of these things cannot be more than a single bit because each xi is just a bit, right? So the potential function can never take a value which is, bigger than 1, but it drops by at least an eta if we failed to produce a good distribution in each of the 1 over eta steps. Well, that's a contradiction, right?
Pravesh.
Yeah.
It's only like dropping, the entropy only drops kind of in expectation over the draw of the xi, no?
Yes, absolutely, yes.
You have to argue also that like you're not getting too unlucky there.
Yeah, so there are many ways, yes, exactly. So
you've gotten enough typical eyes in the subset you chose randomly at the beginning. No?
Yes, but I can also repeat the sampling process many, many times. So I'm only interested in algorithm that runs in time n to the O of 1 over eta. So it's true that the assignment as sampled may not work, but so yeah. So this analysis is in expectation over the assignment sampled for I1 up to I1 over eta. Okay, what that means is that there is an assignment. This means that there exists an assignment to I1 up to I eta that works. And then I can just like brute force it out. Right, so basically arguing an expectation is not so bad. We are completely fine with spending n to the O of 1 over eta time here. Good, that's it. This proves that, in 1 over eta degree O, like 2 over eta degree conditioning, 2 over eta just because, each conditioning is a degree 2 polynomial and I have 1 over eta steps. So this proves that, a 2 over eta degree polynomial can be used to, is a SOS polynomial that can be used to condition mu and find a distribution where the global correlation is at most eta. Okay.
I have a question.
Yes.
How are we sampling the 8 alpha t's?
Good, from their local distribution under the current. So let's see here. The xits are sampled from the local distribution on IT under the mu t under the previous reweighted distribution.
So that's what alpha t is?
Yes.
Okay, good. Thanks.
I did not write. I see the confusion. Okay, let's fix it. Xit sample alpha assignment to xit from the local distribution on IT under mu. Good. Okay, very good. That's it, right? So we've proven that we can generically lower the global correlation to at most eta, and we can find such a reweighting in n to the O of 1 over eta time. Good. All right, this is great. And so all that remains to be done to prove the max cut lemma is to relate global correlation and local correlation on on this low threshold rank graphs that we defined. Okay. Very good. So let's quickly do that so that I get a chance to, do a longer discussion on what the implications are. So in general, our discussion from from a few minutes ago already kind of tells us that, in general, we cannot expect local and global correlations to be related, right, across all graphs. What we're going to do is, only going to imply that this happens for graphs which have small threshold rank, okay? So here, okay, let's see. So I'm searching for my notes correctly here. Okay. Okay, that's just let G be a graph on N, I guess. Okay, that's enough. Okay, good. Let mu be a pseudo distribution on plus minus 1 to the n with GC of mu smaller than eta. Good. Then, oh, wait, stated in contrapositive. Good. Yeah, for some reason, I didn't write down the statement in my notes, so I had to invent it on the fly. I think this is the correct statement. We'll see how it goes. Here's what the statement says. It says that, if you have a distribution, if you have a pseudo distribution mu, and its local correlation is at least beta for some number beta, then its global correlation must be at least, so let's understand this right-hand side expression, okay? So like rho is a parameter here. There is this lower bound holds for all possible rows, okay? Saying suppose, the row threshold rank of G is rank row of G. That's what we define here, right? So, think of using rho, which is like beta by 2, for example. Then this statement says, so let's in fact do that because then it will make sense. So corollary GC mu is at least beta by 2 rank beta by 2 of G squared. Okay, so in particular, if beta is some tiny quantity and the number of eigenvalues of G which are larger than beta by 2 is like this number here, then the global correlation must be at least, beta by 2 R squared. Okay, so now you see like how this is going to be useful. If I start with so here is like a corollary. If GC mu is at most eta, which we can ensure generically, we just saw this process, right? With a 1 over eta plus 2 degree or 2 over eta plus 2 degree pseudo distribution, then this implies that, let's see if I can compute it correctly, beta square must be at most 4 rank beta by 2 G square times eta, right? Still with me? This, I just applied this lower bound here and, combined with the upper bound on global correlation that we can ensure. Together they imply an upper bound on beta, right? And so, this kind of says that, choose eta, which is, much, much smaller than 1 over the threshold rank of G squared, then in some sense, I can ensure that beta square will be tiny. Still good? So this lemma basically tells me that, if I could lower, so in some sense, this lemma is giving me, so this lemma roughly tells us that starting with rank beta by 2g square pseudo distribution. Oh, I guess I used, okay, I guess I can, should have used delta somewhere. Okay, I'm sorry for messing up notation, but let's go on with beta. I guess I used delta for the additive stack we are looking for, but basically this is saying that if I start with a rank delta over 2g squared pseudo distribution, then I can reweight it and lower the global correlation enough so that on my graph the local correlation must be at most delta, and then we already know that independent rounding succeeds. Okay, that's basically the message of this lemma. Let's go ahead and prove it. So we will prove this lemma by first proving a generic theorem about PSD matrices. So let's write down that auxiliary lemma. Say that let M be a n by n PSD matrix such that trace of M is at most n and entries of M are at most 1 for all ij. Good. Then the average of the entries of Mij over the edges of the graph G, okay, let G be a graph on N as usual, the graph that we are looking at so far, is larger than delta, let's use beta, implies that expectation over Ij, so this is the global expectation, Mij squared is at least beta minus rho rank of G squared. So this is some some statement which holds for every positive semi-definite matrix. We're going to apply it to a PSD matrix that comes from our pseudo distribution, but I want to hold off on what matrix it exactly is. Okay, here is what it's saying. Suppose M is a PSD matrix with trace at most n, meaning the sum of its diagonal entries is at most n, and all of its entries are at most 1. And suppose the average of the entries of M, if I take the average only over the pairs of vertices that appear in the edges of the graph, is at least beta. Okay, so think of this as some condition coming from local correlation. We'll see in a second exactly what it comes from. Then it's saying that the global average of entries of M must be somewhat large. Okay, and how large is it relates to the threshold rank at rho of the graph G. Okay, that's what this lemma is saying. We'll prove this lemma in a second. Let's first use this lemma to finish the proof. Okay.
Praveen, how does this M relate to G?
M doesn't relate to G. M relates to the pseudo distribution, but I have not told you about that so far. That's what using this lemma to do the proof would be. So I'm just going to tell you now.
Oh, because the conclusion has something about the rank of G, right?
Yeah. So the correlation. Oh, that's what you're asking. Here, the correlation is across the edges of G, right?
Oh, okay.
So this is E of G, if you will. Okay, saying that if the average entry of M is large when averaged over edges of the graph G, then in fact the average squared entry of M must be large. And how large? Well, it relates to something to do with the threshold rank of G. Okay. Okay, good. So let's use this lemma to complete the proof. So remember what we know. We know that local correlation across the edges of the graph G is at least some number beta, right? It implies that expectation so I'm just inventing this notation xi bar, which just equals, you know, the centered okay, just a shorthand, then, you know, this is what it means to, you know, local correlation, for local correlation to be large, right? Now I'm going to apply Jensen's inequality, and it implies that, oh no, wait, good, fine so far. Still with me? Right, like so what have I used here? I've used that this quantity is at least the average of this correlation quantities squared. So this is using the convexity of the square function, saying that, you know, expect the square of the expectation is smaller than expectation of the square. Okay, good, very good. So now, you know, here is where I use the lemma about the PSD matrices. Let M be the matrix with these as the entries. Okay. Still good? Then note that M is PSD. Why is M PSD? Can somebody tell me quickly why M is PSD? Feel free to unmute yourself. So here is a proof. This matrix is certainly PSD. Right, the matrix with entries pseudo expectations of xi bar times xj bar is PSD. And M is basically the Hadamard product of this matrix with itself. Right, so M equals the pseudo covariance matrix Hadamarded with itself. Hadamard products are, you know, PSD. We studied in the class on the quadratic optimization. So that's what we just quickly used here to note that M is PSD. Good. Now, that's it. We can apply the lemma on this M, right? We can apply, so M is a PSD matrix. And in terms of M, what we know is that the star inequality holds. So star means that expectation ij in E of Mij is at least beta square. Okay. Now, if I apply the lemma about PSD matrices here, what do I get? I get that E ij Mij square is at least beta square minus rho over rank rho of G square. Good. Still with me? So now there is only one trick to do. If expectation of Mij squared is large, what was Mij? Well, Mij is itself the square of the covariance matrix's entries. So this is really a fourth power appearing here. But notice that Mij had each entry of M is at most one. So Mij is always an upper bound on Mij square. So I get that I don't have to take absolute values because entries of M are squares. Okay. And now I'm done. Because, so let's see. So why am I done? So this is, oh wait. did I use this fact too quickly? Let's make sure. No, so fine. So what is the entries of M? So this implies that the covariance of xi and xj squared is large. And wait. Good. So the only thing I need to observe now is something that I explained to you in terms of the information theory business. I explained to you that this is O of IXY. So I wrote it earlier as covariance of xi is at most O of square root IXY. That's what I'm using here. So this implies that EIJ IXI XJ is omega beta square minus rho. That's it. Like I've proven that the global correlation of mu equals omega of beta square minus rho. That's exactly what I wanted. What I have proven that if the local correlation across the edges of the graph G is large, then in fact the global correlation of the pseudo distribution must be somewhat large. Okay, and then if I now start from a pseudo distribution which has a low global correlation to begin with, then running this argument shows that local correlation itself must be small. Okay, now because I only have 13 minutes, let me prove this lemma and then we'll stop for questions. Proof of the, I guess I should number my lemmas. Let's call this lemma technical. Proof of the technical lemma. Okay, let's prove it. Yes, before that, let's find it. There it is. So what does the lemma say? The lemma says, so remember, the lemma says that the hypothesis of the lemma is that for a PSD matrix M, the average of its entries across the edges of this graph G is at least, some number beta, right? And we want to somehow derive that, the average over all possible pairs, 1 less ij less n, mij squared is, at least some beta square minus rho of rank rho G squared. Okay, so we want to somehow derive a lower bound on its, average squared entry, given that the average of its entries across the edges of the graph is, beta. Okay, good, let's do this. So the only thing here is to, somehow use some basic spectral graph theory. And so for that, what we're going to do is note that this equals, so I'm going to write this expression. So this is expression over edges, right? I'm going to write it in terms of the adjacency matrix, the normalized adjacency matrix of the graph G, okay? Agree? Remember, A had the entry 1 over D whenever there was an edge, right? So the way I'm picking you can think of this line as saying that, the way to pick a random edge of the graph is to first pick a random vertex and then pick a random edge incident on it, right? That's exactly what this Aij does. Aij gives weight 1 over D to every edge, incident on I, right? That's what I've done here. Good. Now, I'm going to use that A has a eigenvalue decomposition. A is a symmetric matrix. So A can be written as lambda I, Vi transpose for some vectors V, where, they are all unit norm, right? And lambda I's are the eigenvalues of A. Good. So this equals 1 over n, sum over I, lambda I, And now, I have Aij. A is, if I look at the ith term, it's Vi transposed. I'm taking inner product with Mij, the entry. You can convince yourself that this is same as Vi transpose MVI. Okay, very good. So I have basically, I've used the eigenvalue decomposition of A to write this expression of local correlation in terms of, some eigenvalues appearing here. And now I just want to split this expression into large eigenvalues and small eigenvalues and use the fact that the number of large eigenvalues, of G are bounded for me. Okay, so this is at most I such that lambda I is bigger than rho plus rho. So all other eigenvalues are at most rho. Okay. So here I'm using that all of the eigenvalues are at most rho. So I'm upper bounding all of them by rho. And I'm using that M is a PSD matrix. So Vi transpose MVI is always non-negative. So I don't lose anything if I upper bound it. And I in fact introduced all possible terms, even from 1 through n. I introduced all eigenvalues here because it's still a good upper bound. Right? Because I only added non-negative quantities on the right, so it's still an upper bound. All good?
Why is A PSD?
A is not PSD. M is PSD.
Sorry, okay. Never mind.
So I'm using that because M is PSD, Vi transpose MV is positive. So, on the right hand side, I upper bounded all eigenvalues, which are, all the small eigenvalues by rho, right? Then I had like this expression Vi transpose MVI sitting inside. I just like introduced all possible, I added all Vi transpose VIs, for all possible eigenvectors. It's only an upper bound. Good. So now we are good because so remember that eigenvectors of A are orthogonal. And so another fact from linear algebra, I'm not sure if you proved it on homework, is that if I sum Vi transpose Vi on any orthonormal basis, for Rn, then this equals the trace of M. It's a simple proof, which on a good day I will prove, but I have 8 minutes, so I will not do it. It's a very simple proof, not so hard, but I'm going to use this fact. So on the right hand side, basically I have ended up with expression which looks like I such that lambda I is bigger than rho, lambda I, Vi transpose MVI plus something rho. Now I have the inside expression here is at most trace of M. I have 1 over n appearing. So this is trace of M over n. Remember my hypothesis that trace of M is at most n. So this is at most 1. Good. So what have I gotten? I have gotten that rearranging beta minus rho is at most 1 over n I such that lambda I is bigger than rho. So notice that so far I have used nothing about the graph. All of this reasoning holds true for like every possible graph in the world. Now I'm going to make my first usage of the fact that I know something about how many eigenvalues does the graph have which are larger than rho. I know if this number is R, then I know that there are exactly R terms being summed up here. And I'm saying that the R term summed up here have at least a sum of beta minus rho. So there must exist a Vi such that lambda I Vi transpose MVI should be at least beta minus rho over R times n, where R equals the number of eigenvalues of G which are above rho. Okay, this is the point where I've used the fact that the threshold rank of G is at most R. Good. So remember lambda is at most 1. The eigenvalues of the graph are at most 1. So I'm just going to remember from here that Vi transpose MVI is at least beta minus rho n. Good. Now I'm almost done. So let's see what does this mean. Because I have given you a quadratic form of M which is somewhat large, this means that the operator norm, the operator norm of M must be at least large, at least this quantity. Remember Vi was a unit vector. Now I'm going to use some facts from the homework 0. This means that the Frobenius norm of M is also at least this. What is the Frobenius norm of a matrix? It's the sum of squares of all of its entries. Still good? And so now I'm done. So this means that 1 over n square sum ij mij square is at least beta minus rho over r whole square. All right, it was a race against time, but I made it. So time to go back and pick up the pieces of where I lost all of you. Now that I have a proof written down, I feel much better about myself. So let's do it. So this proof is basically just using the eigen decomposition of A. Okay, and using the fact that it has at most r eigenvalues to just do some simple technical manipulations in some sense. Okay, like the proof itself is not so hard. So let's let me make like 2 or 3 comments before I before I run out of the official time of the class. Then we can take some questions. Okay, so the first thing is, have we designed an algorithm for max cut? On low threshold rank graphs? So how does it look, right? Like, we start with an actual, so we start from a pseudo distribution mu, right? Then we lower global correlation and you find a pseudo distribution which has at most eta global correlation. Now you use the fact that the threshold rank of the graph was at most r to conclude that the local correlation under G of mu prime must also be small. Let's say eta. And then you can independently round. But there is one big problem with this plan. Well, not a big problem because it's very easily soluble, but I want someone to point out the problem. What's the problem with this plan? Like, this is a problem. This is a plan we kind of discussed, and we did all the pieces of, right? We said we can spend n to the 1 over eta time to find a reweighting that makes a distribution have global correlation at most eta. Then we said that for a low threshold rank graph means that the local correlation is at most eta. Then we can independently round, and we at the beginning of the class we argued that that's actually going to work to give us an additive eta approximation. Why am I not done? Okay, so it's late and I have only 2 minutes, so let me mention it. It's like, I started with mu and I had this quantity, right? What does rounding mean? Rounding means that I have to somehow get close to this quantity, the size of the cut that mu thinks there is in the graph. But I modified global correlation. So the independent rounding I do actually matches E mu prime of Fg. And we didn't argue so far that E mu prime of Fg is close to E mu of G. Now there are 2 ways to get around this. There are 2 ways to get around this. I'm not sure this is better because there's like a huge light source behind me now, but I have to figure out some other seating arrangement. But why are we not done here? Well, there are two ways to somehow finish the proof here. Here, one is to actually argue that the argument we did, like this random conditioning argument to lower global correlation, we can somehow simultaneously guarantee that the global correlation is low, while E twiddle mu prime Fg doesn't appreciably drop below E twiddle mu of Fg. This is possible to do, and this is actually how some papers who use this trick argued. But there is a much simpler trick that also works here, and you don't have to do any of this, which is you work with what are called as constrained pseudo distributions. Okay, so in the homework, because we only have time for a homework now, on your homework, actually because a homework is coming out today, I will just post it on Diderot. So let's not make it a homework. So on Diderot, I'll explain to you what a constrained pseudo distribution is and how you can basically do this argument where you can maintain this as an equality. So you don't have to do anything special. You can just simply, under all these operations that you're doing, that we, the reweighting operations that we did in the class today, they will not change the value of this particular polynomial f sub g. So we can actually ensure this. And in that case, this plan is actually, good. This plan actually will perfectly work out. Good. So that is the official end of the class. But I know I was kind of super fast at the end. So, let's do questions. There only there's only one meaning of no questions, right? That I've been going slow in all my earlier lectures, because if if everything that was clear in the last part is actually indeed clear, then I have to speed up.
I can ask a question.
Yes.
Yes. So I think I probably just didn't hear you. So at one point you said there are a sequence of reweightings, and one of them has low global correlation.
Yes.
And so how, like in the actual algorithm, how do you find that?
So I should have mentioned this, but global correlation of a distribution is very easy to compute. Of a pseudo distribution is very easy to compute.
Oh, so you just brute force.
Yeah, you just
the lowest one.
yeah. I gave you an explicit choice of 1/eta reweightings that are supposed to work. Just like compute GC mu for each of those choices, and you can compute it. Why is it easy to compute? Well, because I'm just averaging something that is a pair, averaging the mutual information for every pair, and given the local distribution on the pair, the mutual information is some fixed function of the probabilities, right? So remember that the pseudo distribution gives you complete information about the local distribution on any pair of variables, right? That information is just 4 numbers. What's the probability of 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1? The mutual information between that pair is a fixed function of these 4 numbers. So you can compute that fixed function and average it over all possible pairs to compute the global correlation, right? Mm-hmm. So yeah, so you can simply just compute and check if the global correlation is tiny. Yeah, I should have mentioned that it's an easily computable quantity, but yeah, it is.
Okay, thanks.
I guess there is another way that I can succeed in these lectures when I'm going very fast. I suppose people just tune out. And then, I can race to the finish line. Okay. You can go back and check the proof of this PSD M lemma. It's actually very simple. It's nothing very complicated going on. And I'm sorry I had to rush through it. But I'm sure, once you take a look at it again, it won't be problematic. And I hope that everything else was kind of more or less clear.
Can you explain how you can change a proof so you can preserve the expectation on F-sheet?
Again? Good. The constraint. Why can I do this? So you're saying you're talking about, okay, there are 2 strategies I mentioned. One is to just simply, add FG, the value of FG as a constraint. And I didn't quite explain what that means, but I'll explain to you on Diderot. It's very simple, but I'll explain to you that strategy over Diderot. Let me, sketch this other strategy, which I believe is what you're asking about. So let's look at this. Let's look at this iterated conditioning lemma. Where was it? Here. So in this lemma, you can in fact also ask that twiddle E mu prime of Fg be at least, let's say, twiddle E mu Fg minus some O of eta. And the way you can prove this is, it's just some like simple averaging argument. We argued something holds in expectation. You can in fact argue that in expectation over the choices of the reweightings I made. So they're like, what are the random choices in this algorithm? First is the random choice of, the variables I'm going to condition on, the 1 over eta variables I'm going to condition on. And then it's the assignments that I'm going to condition on for each of those 1 over eta variables. So those are the random choices I'm making. You can prove that in expectation over those random choices, in fact, equality holds. Okay. And then, it's just a simple averaging argument. So, because in expectation things held true, they cannot, like in some sense, for a typical choice that my algorithm will make, both those inequalities should roughly remain true. So this, this follows by just some basic averaging. I can even, okay, I can even,
Okay, thanks. Yeah, I'll just.
I can even try to write down that argument on Ditro if you're interested. But yeah, it's a very simple like basic averaging. Like both these facts will hold true in expectation, and then you're just trying to argue that with like constant probability, some slightly worse version of them also holds, and that's yeah some simple averaging.